Connecting a massive, highly complex network with the absolute minimum amount of resources requires a very precise strategy. Prim's algorithm provides exactly that, a systematic method for constructing a minimum spanning tree from a web of data. It operates on a greedy strategy. This means it evaluates the immediate options and makes the most optimal localized choice at every single step, without concerning itself with the broader network. To understand exactly how this process works, we will execute a complete dry run, evaluate the two different data structures that dictate its processing speed, and finally look at the mathematical proof that guarantees its accuracy. When we apply this logic to massive datasets containing millions of nodes, how fast does it actually scale? And why does a simple, localized choice mathematically guarantee a globally optimal outcome? Simply executing the algorithm steps is a coding task. Understanding its data structure limitations and mathematical certainty is what separates a coder from a computer scientist. This diagram displays our starting state, a 5-node graph connected by specific numerical edge weights, alongside a blank tracking table. We need to connect all 5 vertices for the lowest total cost. We establish our initial conditions by selecting vertex A as the starting point. At this exact moment, our baseline cost is 0. We scan all available edges radiating outward from vertex A. We have 3 options: an edge weighing 2, one weighing 6, and one weighing 3. Applying our greedy strategy, we lock in the absolute lowest weight, edge AB. We update our table's cost to 2 and add vertex B to our visited list. Our pool of available options now expands. We evaluate all unvisited edges branching out from both vertex A and our newly visited vertex B. Comparing the new set of weights, edge AD offers the lowest cost at 3. We lock it in, adding D to the visited list, and update our running total to 5. We rapidly execute the remaining iterations using this exact same logic. We lock in DC at a cost of 4, and finally BE at a cost of 5. The graph is fully connected, yielding a final total cost of 14. Notice what happens if we attempt to select an edge that connects 2 nodes already inside our visited list. Doing so creates a closed loop, or a cycle, which strictly violates the definition of a spanning tree. This step-by-step localized evaluation works flawlessly for a small 5-node network, but scanning every single available edge becomes an immense operational bottleneck when applied to millions of data points. The algorithm's logical output remains exactly the same. However, its processing speed is entirely dictated by the underlying data structure chosen to store it. This animated grid represents the adjacency matrix implementation. We map the graph onto a 2-dimensional grid, where the rows and columns represent vertices, and the intersecting cells display the edge weights. During a single iteration, finding the minimum edge requires the algorithm to linearly scan every single vertex across a row. This processing step takes O of V time. To build the complete tree, we multiply this single iteration scan by the total number of iterations required. This yields a final time complexity of O of V squared. Because storing this grid requires V multiplied by V memory cells, the spatial footprint also carries a space complexity of OV squared. The matrix implementation forces massive redundant checking. It is highly inefficient for sparse networks, but perfectly suited for dense graphs, where almost every node connects to every other node. To eliminate that redundant scanning in sparse graphs, we can switch our data structure to a min heap, also known as a priority queue. This diagram shows an adjacency list feeding directly into a min heap. The core mechanic of a min heap is that it automatically organizes data so the smallest available edge weight always floats to the top of the structure. Because the smallest edge is always waiting at the apex, extracting it and reshuffling the remaining tree takes logarithmic time, or O log V. Multiplying this extraction cost by the total number of edges processed drops our final time complexity down to OE log V. The space complexity is also reduced to O of V plus E. The golden rule for algorithmic scaling is that data structure choice is entirely context-dependent. Use adjacency matrices to brute force dense graphs, and min heaps to efficiently navigate sparse networks. We know exactly how the algorithm scales. Now we must mathematically prove why its localized choices never lead to a global dead end. Look at this graph, divided down the middle by a dotted vertical line. This illustrates the cut property. We conceptualize the network as two isolated factions, visited nodes on the left and unvisited nodes on the right. At any given step, multiple potential paths physically cross this dividing line to bridge the gap. Prim's algorithm strictly selects the single crossing edge with the lowest possible weight. To test if this choice is truly optimal, we use a logical tool called the exchange argument. Assume a hypothetical scenario where a perfect minimum spanning tree exists, but it rejects Prim's edge. Instead, it crosses the cut using a heavier, more expensive alternative. Now, we execute a mathematical exchange. We forcefully remove that heavy edge from the tree and plug Prim's minimum edge back into its place. The graph remains fully connected. No cycles are created, and because we swapped a heavy edge for a lighter one, the total mathematical weight of the tree strictly decreases. Because exchanging any alternative path for Prim's minimum edge always improves the total cost, it is mathematically impossible for Prim's localized greedy choice to produce anything other than the globally optimal minimum spanning tree. As displayed here, the architecture you select dictates your speed. The matrix yields O of v squared, while the min heap yields O of E log v. Regardless of the structure, the core operational mechanism is identical. Iteratively add the cheapest safe edge that bridges the gap between visited and unvisited territory. This step-by-step process is shielded from error by the mathematical certainty of the cut property. However, there are strict limitations. The algorithm entirely breaks down if the graph is disconnected, or if the edges lack numerical weights to compare. Prim builds trees outward from a single point. Our next major algorithmic milestone, Kruskal's algorithm, approaches this exact same problem by sorting edges globally and utilizing disjoint sets.